This lesson is for Chapter 2, Section 4, a library of parent functions. If you guys would all please turn to page 198 in your book and get your notes out and ready to go, we'll get this one started. All right, one of the kinds of functions that we're going to be taking a long look at, you guys have done plenty of these in the past as well, are linear functions. Okay, linear functions, of course, are going to be those graphs that end up looking like straight lines. Things like y equals mx plus b is a linear function. Our point slope form that we were playing with the other day would turn into a linear function for us as well. Horizontal lines, vertical lines, those are linear as well. Horizontal ones are the only ones that are functions though, because that vertical line is not going to pass our function test. So linear functions, they can be positive slope, negative slope, or slope of 0, but they will be definitely straight lines. One thing that they're going to do in this section is have us come up with a linear function if they've given us a couple of function values. So in checkpoint number 1 at the bottom of page 198, it says write a linear function for f of negative 2 equals 6 and f of 4 equal negative 9. Now, if you take a close look at these values that are given to us in this particular problem, negative 2 in this problem right here is in the x spot of the f of x, correct? And then we know that f of x is the same thing as y, so they're telling us that y, like that whole thing, f of negative 2, is equal to 6. So you can take that chunk they give us in this problem here and you can rewrite it as its ordered pair. We're going to go to the other one and we're going to do the same thing. The 4 is sitting in the x spot. F of 4 is equal to negative 9, so negative 9 is technically our y value. Okay, so from these two things, we in the past in Algebra 2 have written linear functions from two given points. First thing we're going to do is we're going to calculate a slope. Okay, so y2 minus y1 over x2 minus a minus 2 gives us negative 15 over 6, or negative 5 halves for our slope. Now you can use either of the ordered pairs that we came up with, either negative 2, 6 or 4, negative 9, and you can fill in the y equals mx plus b format, or you can use that point slope thing. I'm going to go ahead and I'm going to use point slope. I'm going to pick negative 2, 6. It would not matter which of these that you chose, but if I fill in point slope now, I have y minus 6 is equal to a slope of 5 halves times x minus a minus 2. Start simplifying. Negative 5 halves times 2 is just going to be a negative 5. Move over your 6. And here is your linear function. Ready to graph. You can see your intercept, you can see your slope, it's ready to go. Quadratic functions are going to be graphs that are parabolas in shape. Quadratic functions, remember, are going to come from squared functions. So in other words, they're going to have an x squared value in them. The general form or the general shape of a parabola just simply looks like that. They could be upside down, they could be tipped sideways. We will explore in the future here real soon what makes them do that. But the squared functions turn into this shaped graph. Cubic functions, we talked about this a little bit just the other day. If you have an x cubed term in your function, it's going to be this kind of curvy curlicue kind of thing. Okay, again, we're going to be sliding them, flipping them, transforming them, but that'll come up in our next section. For right now, we just want to recognize that this is the kind of curve that we're going to get. It's symmetrical. The parent function passes through the origin. But anyway, x cubed ends up looking like this shape. If you have a graph of a square root function, okay, square root functions are going to be a version of, if we have square root of 0, we get 0. Square root of 1, we get 1. Square root of 4 is 2. Square root of 9 is 3. Do you see how it's going to kind of level out? If you look in your text at the parent function for square root, it kind of does this thing. It's going to gradually increase as it moves to the right. A reciprocal function. All right, now a reciprocal function means that our variable is going to be flipped. So an example of what a reciprocal function might look like is something like f of x is equal to 1 over x. Reciprocal functions, because they're going to have denominators with variables in them, we're going to get some of those unknown, or not unknown, undefined values for x. So for example, on this one, we can't have 0 in that denominator. So this is going to be a split type of curve that never is going to hit x equals 0. It's just going to kind of curve around it. All right, so your reciprocal function is going to be split like this with some asymptotes in between that we can never get to. We're just going to near them. And we'll explore more of these later and do some graphing of them. Absolute value functions are going to end up being shaped like a V. Again, the V might point down, point to the side, and we'll explore what's going to transform them and move them like that. But your absolute value functions are going to be V-shaped. Greatest integer function. Now, this one is a newer one. I'm not sure if you study greatest integer functions in Algebra 2 or not. I know that they are dealt with in pre-calc, but some of you guys haven't been in that class before. It's not too terrible of a concept. Okay, the greatest integer function says that the graph will appear like steps. The notation, and it's kind of a new form of our bracket, kind of a double-barred bracket, means the greatest integer less than or equal to x. Okay, now what does that mean? Well, the easiest way I felt to show you this was to actually come up with a table of values for this particular function. I pulled one out of our homework page. It's example number 3 found on page 203. But it says g of x is equal to the greatest integer less than or equal to x minus 1. Okay, so that's our whole function. It's a mouthful, but I'm just going to build you a table of values. Okay, so let's do an x and a g of x chart. Remember, g of x just means y. If I choose 1, and then I'm going to do some decimal, 1.3 I'm going to pick, 1.7, and then I'm going to go 2, and I'm going to do a few decimal values, including a 2 as well, so that you can get an idea of what this kind of graph is going to do. Now, if I put my first x value in, the integer the greatest integer less than or equal to 1 is 1. Subtract 1 then, 0. What if I put 1.2 in? The integer greatest, or the greatest integer less than or equal to 1.2. Well, the greatest integer less than or equal to 1.2 is a 1 again. I do 1 minus 1 again, and I'm going to get another 0 in my output. Okay, then you're going to put 1.3 in. What's the greatest integer less than or equal to 1.3? 1. I have to subtract 1 in my function from that again. I'm going to get another 0. I will for 1.7 as well. Now let's play with the 2. My next x value that I put in my table was 2. Place 2 inside the bracket. What's the greatest integer less than or equal to 2? Well, that's going to be 2 itself minus 1. I get a value of 1 now. Now put a 2.1 in. Maybe you're starting to guess what's going to happen here. The greatest integer less than or equal to 2.1 is 2. I subtract 1 again, I'm going to get another value of 1 as an output. So for all these 2 point somethings, We're going to have to revert back down to 2 because that's the greatest integer less than or equal to those 2 point whatevers, and then subtract 1. We're going to end up with an output of 1 for all of them. How does that end up looking when we graph? All right, well the point 1, 0, that's easy enough. And then I need to graph the point 1.10, which is just a little bit further over, 1.3, 1.7, until I hit the 2, which pops up to a value of 1. Okay, so how do they show that? This is going to be hard because my pens aren't lining up very well. You're going to have a solid line and then an open circle. And then above it, we end up with this step, and it'll be open. And it's going to keep stepping up like that all the way up our graph. Every time we do x values and decimal versions of them, it's going to step up like this. Okay, so for all of your 3s and 3.1s and 3.3s and 3.7s, you're going to end up going with 3 minus 1 and getting 2s. Okay, so you can see that whole chunk where the x values are 3 something, we have a flat line at 2. All of them would result in a value of 2. We can talk about that one some more in class as well. I'm sure that's the new one. And we'll try to make sense of that greatest integer function together. I talked about this page number in class, page 202. All right, all of our parent functions are summed up with a nice diagram on page 202. Okay, so keep referring back to that. I think you're going to find it very helpful. All right, back up the train one page again, back to 201. We're going to evaluate this function for a few given values of x. All right, so we're given -3/2, a 1, and a -5/2. So let's see if we can't play around with another one of these greatest integer functions. All right, so if I have f of x equals greatest integer of x plus 2, what are we going to get for that? All right, well, let's put our first x value in. -3/2 plus 2. -3/2 plus 2 is 1/2. Everybody agree? So what is the greatest integer less than or equal to that? Okay, so the greatest integer less than or equal to that is 0. Okay, greatest integer. Remember, integers aren't fraction or decimal values. We're going kind of like going to the next lowest whole value from where our 1/2 is at. Okay, so the whole number less than or the integer underneath a half is 0. Okay, let's play with 1. Start all over again. You're going to put in 1. Okay, so now I want the integer less than or greater than 3. Well, 3 is an integer itself, so we will get 3. Okay, so integer less than or equal to what we find. One more value, -5/2. Okay, -5/2 plus 2. We're going to get a -1/2 from that. So what is the greatest integer less than or equal to this? We'd have to drop to -1. Okay, -1/2 isn't an integer itself, so we drop down to the next integer, and that would land us on -1. So there's the values evaluating that function for those 3 given inputs. One last kind of function is called a piecewise defined function, and it's because it comes in pieces. All right, so there's certain values or certain inputs that will have us using one function, and then there will be, once you cross over to a different chunk in your domain, you're going to switch and use a different function. Okay, so let's take a look at this one. Notice that it has 2 pieces. You've got this function and you have this one. 2 different ones, because as this one says, for any values that are less than or equal to -4, you're going to plug them into -1/2 x minus 6. Now, if you happen to have a value that's greater than -4, you're going to plug that into x plus 5. So you don't use them both. Okay, you look at what your input is, you plug it into the appropriate one. Not both of them. You find the appropriate one and you plug it in. Okay? So what I decided we should do with this one is we're just going to pick some values. Okay? So let's play with this and figure out which function we would use based on a given value to plug in. How about if we took -8? So I'm going to pick a few of them that are less than or equal to -4. And then I'm also going to pick a few of them that are greater than -4. So maybe -3, oh, 0 is always nice, and maybe a 1. Okay? So these three values, okay, -8, -6, -4, all fit the domain of x is less than or equal to 4. Everybody agree? So that means I need to use this function. Okay, so if I plug in -8 to -1/2 x minus 6, -1/2 times -8 is 4. 4 minus 6 is -2. Gives me a point I can graph. Do that with -6. Again, it's going to go into that same function because, again, it is less than or equal to -4. So -1/2 times -6 is 3. 3 minus 6 is -3. -4 still fits that top part of our function. 1/2 times a -4. 1/2 times -4 is +2. 2 minus 6 is -4. Now at -3, we are no longer in that domain. We are no longer less than or equal to -4. We are greater than -4. So now these inputs fit this piece. We're going to use the function x plus 5 now because these values are greater than -4. Okay, so plugging in -3, I'm going to have a -3 plus 5, which is 2. Plugging in a 0, I have a 0 plus 5, which is 5. And plugging in a 1, 1 plus 5 is 6. So let's go over and start graphing our points. -8, -2, -6, -3, -4, -4. Okay, then we had -3, 2, 0, 5, 1, 6. Now, these are going to come together. If I were to pick things like -3.2, let's even do that. If I put in -3.2, I would end up with 1.8. So -3.2, I would have 1 point. I'm going to edge down here a little bit lower. Do you see how if I do more decimals, -3 point somethings, I'm going to edge closer to a 1. But I'm never going to be able to hit it because that would be a -4. I can't use -4. I have to stay greater than -4 in that top piece. So I'm going to put an open circle there just to hold it and give me a start. This one gets a full circle at -4 because that's the piece of the function that I actually use with -4 itself. Okay, so there's our graph of that piecewise function. Table of values is going to help you out a lot with that. All right, your problems for your practice are going to come off of pages 203 and 204. It's a short one. Okay, so do a bunch of them. Try to get familiar with what the graph is going to look like. Practice loading them into your calculator for problems 15 through 26 and so on. And then we can go over any questions that you might have when you get to class.